Jacobian every time you change coordinates. But at the same time, the metric also changes. Well, if you remember, the metric Gij, well, it's a tensor of type 0 to covariant tensor. So the metric in new coordinates will look like this. G, K, all X. Well, let me write it this way. Yeah, okay. This is I prime, J prime. dxk, dx prime 1, dx J. And again, there is sum over K and sum over L because they are repeated. So you have this formula because, well, it transforms like a tensor of type 0 to covariant tensor. And so if you take the determinant of that, well, let me put prime here. Ij. So prime means it's a tensor in new coordinate system. Then, well, you get determinant of this matrix squared because there are two of them. So you get determinant dx by dx prime squared, and then the determinant of g. Right? And so if you take this to the power 1/2, then you get rid of this. And so if you now take this and multiply by the square root of the determinant, then this Jacobian will cancel exactly this one because this is Jacobian of the matrix dx prime by dx, and this one dx by dx prime. That's an inverse matrix. Dx prime by dx is equal to dx by dx prime inverse. And therefore, this Jacobian cancels that, and you get exactly the invariance of the volume element. So that's why you need that square root in the volume form for the manifold. Anyway, that's the divergence formula. Okay. Local formula. Now, let me remind you. Well, I want to write a divergence theorem, which is an integral. Well, the general Stokes theorem, those of you who haven't seen it, you'll see it in geometry, which is coming. It looks like this. Very simple. You choose that. Where M is the manifold, that's the boundary. This is the form. This one is exterior derivative. And that's some form, and that's exactly, well, that's what it is. It is so general that it includes all formulas that you know, like the Gauss formula and Green formula and Stokes formula and all the other formulas in any dimension, 2, 3, 4. So in particular, this leads to the following. Okay, well, just a second, let me explain. Let me try it. So you want to have a formula how you integrate by parts, basically, under manifold. So you want to be able to integrate by parts. And so you know how you would do it. You basically do something like this. Well, you have some volume element. Well, when I write dx, then it is dx1 dxn. It's just And then you have di, well, let's say ai. Well, it looks like a divergence, right? So then you know that this is equal to the x hat. These are coordinates on the boundary, x hat. And then ai, that's the normal. To the boundary. So this is standard, right? So you've seen it before. Basically, the integral of a divergence is equal to the normal component of that vector. So, well, when you generalize it to curved manifold, then this looks like this. Well, let me call it this dV. Well, this dV is the volume form, I think the Riemannian volume form. And then you have the divergence of a vector field. And here is ds. Well, that's basically dV is g to 1/2 dx. What is this ds? Well, that's the volume on the boundary. So it is g hat to 1/2 dx hat. Well, this hat means that this is a metric on the boundary. It's, well, it is induced metric on the boundary. Well, it's done exactly the same way. It's the Riemannian volume element on the boundary. And then here you'll get, well, you get exactly when this is the normal to the boundary. Well, this is your M, this is your boundary, and then that's what is M. Okay, so that's the formula. And it turns out that you can integrate by parts by using covariant derivative instead of partial derivative. And then you could actually do it in general. Let me write this. Well, there is another formula that's related to that. Well, let's say properties. Suppose that you look at an integral like this. Well, you have a vector field x, and you take an inner product with the gradient of some scalar function. So the gradient is another vector field. So basically, what is here is dx g to 1/2. Well, there is xi. This gradient will give you d I u. Well, that's what it is. Well, of course, you would write it like with the metric gij xi gradient u, the component j, but this together with that is exactly this. Okay, so then this is equal to, well, and suppose that function u, so that this vector field and the function have compact support, which means that on the boundary they are zero. So that's why you don't have the boundary terms in that formula. Then this is equal to minus an integral. Well, you take that gradient, basically bring it here, and you get the divergence of x times u. So I integrated by parts once. So well, if you take this and you move it on that, you get minus derivative of this thing. And then you have to reinsert g2. Well, basically, look what it is. This is dx g to 1/2. The divergence is g2 minus 1/2 di g to 1/2 xi u. So you see that this and this cancel each other. And you just go d acting on this. It's exactly like taking this d and putting it on that. Okay, and so you have this formula. This is equal to that. So this is another way how you could define divergence. You could say, well, for any function u, divergence is something that is related to that. Okay? So that's one formula. Well, and then, if you assume that they don't have compact support, in other words, on the boundary they are not equal to 0, then you will have an additional term. You'll have the boundary term when you integrate by parts. Namely, well, this quantity is equal to di g to 1/2 xi u minus u di g to 1/2 xi. Right? So this part gives you the same term that I talked about, and this one, it's an integral of that. That gives you the boundary term. So basically, this is negative integral over m dv, the divergence of x u, and then there is that piece which gives you the integral over the boundary ds. Well, this basically this becomes the normal, and that's it. This is, you see, that just becomes the normal vector. And so this g to 1/2 with that gives you ds, and you get ni xi u. And so that's a little more general formula there. Well, of course, I mean, you can write this a little nicer by saying, well, it's this inner product, right? Well, that's the same thing. So, because you need to know the normal. So, and then, I mean, if you take this plus this, that will give you that boundary term. Okay, that is it in terms of divergence. And any questions? Yes?
When you have a minus sign for the divergence from that formula,
Yes.
I was thinking of the gradients is already perpendicular to the vector that you're doing the product, so you don't need to have like a negative sign outside. Is that right?
No.
No.
Why do you say gradient is perpendicular? Gradient is perpendicular to the level curve or level surface of u. So why? Why is that important?
I don't understand why the negative sign.
Well, it comes from the standard integration by part formula.